This lecture is now devoted to the the frequency response analysis of dynamical systems. The idea behind frequency response analysis is that, as you have already seen, it contains a ton of information. I now need to explain to you the rules in order to draw the proper frequency response representation of a dynamical system. For that, I assume I have a dynamical system which is given by a transfer function h of s. That transfer function, I assume, is, to start with, stable, and it is excited by a signal u is equal to either something like cosine omega t, or more generally, I prefer to say that it is excited by a signal which is e to the j omega t. We have already seen several reasons for why we want to use this kind of excitation instead of that kind of excitation, even though e to the j omega t is cosine omega t plus j times sine omega t, and therefore is complex. The only thing that needs to be done at the output, if the input is u is equal to e to the j omega t, and if I call this output y, is to say that y of t will be y1 of t plus j y2 of t, and say that the real part of the response corresponds to the real part of the excitation, and that the imaginary part of the response corresponds to the imaginary part of the excitation. In other terms, what you will get at the output for the excitation cosine omega t will be y1 of t. And by the way, when u is equal to sine omega t, then the response will be y2 of t, all things being real and physically significant. So h of s is the transfer function, of course. And what we have seen is that if we neglect the transients, that is, the time for the system to establish itself into a steady-state behavior, then the output y will be something like h of j omega where h of j omega is h of s with s equals j omega. So this is just a particular set of values of h, the transfer function, taken when s travels along the j omega axis. So we now need to have some more concise information about h of j omega. So for example, what we can say is that if u, and of course this is when u is equal to e to the j omega t. So you see that the clearly pertinent information in all this is h of j omega. H of j omega is most easily plotted, okay, either from the math expression or from measurements precisely obtained with this kind of excitation. It is very powerful, and the MATLAB function or the Scilab function that implement the plotting of this transfer function is named Bode. Why? Because the Bode plots are the ultimate way of plotting, or one of the ultimate ways of plotting the system. How does that work? On the one hand, we plot the amplitude response, which is the modulus of h of j omega versus omega. On the other hand, we plot the phase, which is the phase of h of j omega counted as a complex number versus omega. Remember, the phase is computed as follows. You have the real axis here, you have the imaginary axis there. If your dot is here, the phase is the angle that the real axis makes with the complex point written in this plane. The phase varies in principle from 0 to 360 degrees. However, we won't say 0 is equal to 360 degrees. Instead, we will unwrap, the frequencies. These are not the frequencies that we unwrap. We unwrap the phases. That is, we'll encounter phases of minus 90 degrees, minus 180 degrees, 360 degrees and above 720 degrees, which is twice as much, and minus 360. Though we will usually stay in the range of small phases for practical purposes. Now, if I call Scilab and I define my transfer function as a second order transfer function, as for example, 1 divided by, or 1 over s times 1 divided by s squared. Oops, let me add some things here. S squared plus 0.5s plus 1. I forgot the multiply here. So my transfer function has one integrator and then multiplied by a second order transfer function. I can now plot the body plot by first introducing the system cis equals syslin of TF. I keep forgetting parameters, and which looks very much the same. And now I can plot body of cis. This command will actually do exactly what I say, modulo a couple of additional pieces of information. So what you see is the magnitude of the transfer function, the integrator multiplied by the second order transfer function, and this magnitude is plotted against frequencies. Notice that in our case the frequencies are indicated in hertz. In the MATLAB, the frequency could be indicated in hertz or in radians per second. Since omega is usually expressed in radians per second, when we have omega tilde in hertz, okay, we have that omega tilde is equal to omega divided by 2 pi. Such is the conversion between omega tilde in hertz, that is in number of oscillations per second, and omega in radians per second, which counts the number of radians it does per second. And indeed, 1 hertz is 1 oscillation per second, which is 2 pi radian per second. So sometimes I will need to juggle between the two representations as I go from my derivations, which would be essentially in radians per second, and my plots, which will be essentially in hertz. Likewise, the phase is plotted as a function of the same frequency, also expressed in hertz. And what you see is what I was indicating, which is that we have unwrapping on the phase, which starts at minus 90 degrees and eventually drops to minus 270 degrees. So all this looks good, except that the axes that are being used may not be very familiar to you. If you notice here, the spacing between the values of omega is equal, but it is the spacing between the orders of magnitude of omega which is evenly spaced. In other terms, this axis here is a very nonlinear scale of omega, ranging over a very broad range from 10 to the minus 3 hertz to 10 to the plus 3 hertz. Think of it. This is 1 million in factor between the numbers here and the numbers there. This astonishing dynamic range that is that is how it is named, or bandwidth, is what justifies plotting the frequency response using these so-called logarithmic scales, which spaces out different scales evenly along the axis. Phase-wise, we plot the phase as we see it. It is in degree, it's a linear scale, there is no problem. Now the magnitude is plotted in this weird unit named the decibel, dB. What is this? Well, it is in spirit the same as this scale. It is in spirit the same as this scale. That is, we have found that magnitudes tend to go from very large to very small values over the range of useful information that we need to get about the system. And so, as a consequence, we chose, and this is an electrical engineering defined thing to begin with, but it has been adopted almost everywhere. We define the decibel as follows. For number x, which is positive, x dB. So x expressed in decibels is equal to 20 times log in base 10 of x. This is an important information that you need to remember. Indeed, that information is what will allow you to interpret these plots, okay, and to be able and plot them as well. Now, the reverse expression is x is equal to 10 to the power x dB divided by 20. Now, what you can see is a few things. When x is equal to 10, then x dB is equal to 20, because log 10 of 10 is 1. When x is 1, x dB is 0, because log 10 of 1 is 0. When x is equal to 0.1, then x dB is equal to minus 20. All these numbers then make sense. This is about a factor 10. This is about a factor 100. 50 dBs is going to be approximately a factor 200. 0 dB, that is when the value of the frequency response of the transfer function crosses the 0 dB, corresponds to a gain of 1. And then likewise, we have lowering things. Here we have the transfer function, which actually remains always positive, but which gets orders of magnitude smaller. I can probably look at a few things more precisely to do an up-close view of what I am talking about. you see that the scale automatically changes. And then we have a scale of 0 dB, which is a gain of 1, minus 20 dB, which is a gain of 0.1, minus 40 dB, which is a gain of 0.01, and 40 dB, which is a gain of 100. We can therefore understand how big this transfer function is by just interpreting those numbers the way they should. Moreover, what we see is that the effect of using effectively a log scale because this is what plotting the log of a quantity as opposed to the quantity itself means, allows us to consider the value of the transfer function, the frequency response, over a very broad range of scales, just like the log plot of omega can be seen as able to represent omega over a very broad range of scales. Now, what I would like to do with you is go over some of the rules to plot a Bode plot. Those rules are made a little bit obsolete by the fact that we have access to computer tools such as MATLAB or Scilab, but nevertheless, they are useful for you to recognize what goes on at once. Before I go into further details, I would like to see if we can plot Bode plot using radians per second instead of hertz. This must be possible as soon as we can do that. Hold on a second. So what do we have as options? Now this thing really insists on plotting things with hertz. Okay. Unless I can use this frac thing. Okay, so they seem to be insisting on hertz. Well, we'll be sticking to hertz on our plotting capability, and I may use radians for my explanations. So, how does it go? Well, what I would like to do is plot with you a few transfer functions. The first one would be h of s is equal to simply 1. Now, this is the transfer function of an all-pass filter, and when we plot the magnitude in dB, which we will call in short HdB, as a function of omega, and I need not space omega out very precisely. And you see here, I use omega expressed in radians per second. I let you do the conversion to expressing omega in in other units. Okay. Then my transfer function, if this is 0 dB, and that is 0.01 radians per second, okay? The 0 is for the vertical axis. For the horizontal axis, this is 0.01 and 0.001 will be flatly the 0 line. Indeed, 20 log of 1 in base 10 is 0. Now, what do I need to add? These decibels. That we are talking about. They are the same as in your stereo amplifier. And they are the same as in the noise measures or the measures of loudness. You remember probably hearing about the 80 decibels threshold above which it becomes painful to hear. Those decibels are in fact the same units as those used here, but in order to measure intensity of noise, as opposed to intensity of a transfer function. This is not a surprise. This is partly where the thing originated before it was found to be useful in a whole bunch of things. So if I go to the web for a second, I can. Okay, hold on a second here. I have too many of those. I can just go to the web and get that information. Okay. Oh gosh. All right. So now what I want is information about noise intensity. So sound intensity in this case is the sound power. And what I want is to convince you that at some point some decibels will show up. And sure enough, this is the decibel formula here. Okay. Notice that this formula is slightly different since they use 10 log 10 instead of 20 log base 10. The noise intensity is measured as the dB intensity of whatever noise power is measured over whatever reference sound intensity is chosen. So that shows, to some extent, the link that exists between what I am talking about for your mechanical systems and what you could be talking about or hearing about in the literature. Let me add that the systems that we are using is the class that we are learning is equally useful to do sound control as it is to do other kinds of controls, including the mechanical system. So we can do both. You will learn stuff that is useful for those of you who want to do audio engineering. So I'm still looking for that scale of pain. And here it is. Okay. So at 10 to the minus 12 watt per meter second, which is the reference noise, okay, we cannot hear it. We are at the limit of being able to hear anything. And it is at 0 decibels because it's the ratio of this noise intensity over the reference noise intensity, which is precisely this one. Now, you have these different things that may help you understand the link between decibels and what they mean in terms of noise. And what you see is that as the number of decibel grows linearly, the meaning of it grows exponentially, since at some point for 100 decibels, we are basically deafening ourselves with a Walkman or a iPod now, okay, and only 40 decibels later, we are hearing a military jet taking off, and 20 decibels later, there is twice as much as the noise of a vacuum cleaner, but expressed in decibels, the eardrum blows. So it is this scale which, as you see, can really compress the scale of phenomena happening in nature, as well as the scale of phenomena happening in our mechanical systems. What do we do with this? Well, we now go into further plots. Before that, I want to mention the value of 2 in decibels. 2 is equals to 6 dB. For those of you who are used to hearing about audio engineering, the 6 dB line is probably well known to you. It corresponds to when a particular response is either multiplied or divided by 2. And the 6 dB is often considered to be the threshold beyond which the response is an order of magnitude smaller than the nominal response, okay, the nominal value, because it is in fact divided by 2. We will see a lot of uses for this little formula here. Of course, please convince yourself that square root 2 in dB will be just 1/2 of this, which is 3 decibels. Okay? While at the beginning this might be a little painful units for you to work with, they will eventually become a natural and expected of you. So let's look at the case when h of s is equal to 10. Well, the story is pretty much the same. Okay, when h of s is equal to 10, we will have the same scales here along the x-axis. And again, I will represent them logarithmically scaled. Okay. And then I will have my vertical scales that will be, for example, minus 20, 0, 20, 100. And these will allow me to say, oh, a factor of 10, that's 20 dB. It is right there. Okay? And it really corresponds to shifting this guy up by 20 dBs. When I take h of s and I go to 10 times h of s, I shift up by 20 dBs. By the way, this is not 100 here. This is 40. Okay, and I got lost because 100 in dB is indeed 40 dBs. Okay, so if h was 10, we multiplied by 10, we shifted up by 20 dBs, and we effectively get 100. Now, what we can do is look at the we can use more complex transfer functions to make things more fun. What will happen is if h of s was equal to 1 over s instead of something constant. Well, let's look at the formula. Okay, first of all, h of j omega is equal to 1 over j omega. So two things here need to be computed, unlike the previous cases. First, h of j omega, which you will have no problem computing as 1 over omega. Second, the phase of h of j omega, which you will obtain by saying that h of j omega is also minus j over omega, and therefore this will be minus 90 degrees. In the previous case of constant h, for h is equal to 1 or 10 or whatever positive number, the phase of h was clearly 0. Okay, so let's write h of j omega in decibels. H of omega in decibels will be 20 log base 10 of 1 over omega, which is minus 20 log in base 10 of omega. Okay. Now suppose that we plot h of j omega in decibels versus omega in decibels. Okay. We would have that h of j omega in decibels divided by omega in decibels is equal to minus 20 log 10 of omega divided by 20 log 10 of omega. It is equal to minus 1. That is the minus 1 slope that I erroneously talked to you about a lecture ago. Erroneously because I forgot to introduce this notion to you. But I wanted to quickly go to frequency responses instead of and explain what they meant, and instead of going through the gory details of them, which I am doing now. Now, here is something that people do. Turns out people don't like to express omega in decibels, but they do like express the gain in decibels. Don't ask me why. This is the way life is. Therefore, what we're going to have to do is do this kind of weird plots. Okay? First, where omega will be plotted on a log scale, but will be represented in radians per second. And the transfer function will be plotted in dB, but, you know, we will also use the same log scale as omega in order for us not to get too lost. Here is how our representations go. For h is equal to 1 over omega, 1 over j omega. So we can take care of the phase right away. Okay? We can use a log scale for omega, whereby we start at 0.01, then we do 0.1, then we do 1, then we do 10, then we do 100, then we do 1000 in radians per second, which is a little bit different from the hertz that you're going to see, but which is much more useful as far as hand manipulations are concerned. So we are plotting this versus the phase of h of j omega versus omega. We have seen that the phase is minus 90 degrees. So I would put 0 here, I will put minus 90 degrees there, in such a way that my phase will simply be a horizontal line here. Now let's go to my gain here, okay? And here's what I'm going to do. I'm going to put a double scale along the y-axis in decibels and in magnitude. The scale in decibel will be linear, the scale in magnitude will be logarithmic, but they mean the same thing. I use the same semi-evenly spaced omega expressed in radians per second, where the spacing is logarithmic, 0.01, 0.1, 1, 10, 100, 1000. Let me see what it would look like in dB. That would be 0 dB, that would be 20 dB, that would be 40 dBs, and that would be 60 dBs. That would be minus 20, and that would be minus 40 dBs. Now, on the vertical scale, I do the same. I call this gain, I use this vertical scale here, and I will need to use another color in order not to mix up my horizontal scale with my vertical scale. This will be a gain of 1. That will be a gain of 10. That will be a gain of 100. Okay? That will be a gain of 0.1. That will be a gain of 0.01. In dB, that corresponds to 40 dB. Let me try another color. That will be 40 dBs. That will be 20 dBs. That will be 0 dB next to 1. Then that will be minus 20 dBs. And that will be minus 40 dBs. I said that expressed in decibels, both along the omega axis and along the value of h axis, the y-axis, okay, its magnitude. When h is equal to 1 over j omega, then the plot of the magnitude is a negative slope with slope minus 1. Okay? Which means that if the gain at 1 radians per second is in fact 1 over j, or in other terms, in magnitude 0 dB, all that we need to do in order to capture h at other frequencies is to plot the line which has a slope of minus 1 on the scale of decibels or on the scales of omegas and h, but log scales, okay, in such a way that my response looks like this, okay. We have several ways of calling it. One of the ways is this minus 1 slope that we've talked about. Others prefer to talk about minus 20 decibels per decade. Why decade? Because a decade is a jump of a factor 10, but the jump of a factor 10 is a decade is 20 dB. So we're talking about the same thing, because minus 20 dB divided by 20 dB is minus 1. You will see these two expressions very often in your professional lives, whether or not you do controls and dynamical systems the way they are presented in this book. And so I intend to familiarize yourselves with this notation right now. This finishes my lecture. Thank you.